Now we get into the assumptions for running a correlation. So you've collected your data, you have your variables. Typically, you already know what type of test you're going to run before you collect your data. But let's say we've collected our data and we now need to determine if a correlation is actually appropriate for what we have collected. So these are the assumptions. These are things that you have to meet before you can actually run the test or accept the results of your test. So random sampling should always be a thing when we're collecting our data. So that means we haven't handpicked anybody from our population. Our data should be normally distributed with no significant outliers, and I'm terming significant outliers as anything that's outside of 3 standard deviations. So reason being is that skewness can affect the line of best fit. Usually when we have outliers that are outside of 3 standard deviations, that's when we notice the largest effect on the correlation results. So I'm deeming no significant outliers outside of 3 standard deviations. To do or to check our normality, we can use our z-skew, z-curt calculations in addition to a Shapiro-Wilk test. So these are going to kind of be the 2 methods that we'll use for the rest of the semester. We also need to determine if we have any outliers. So we'll go through examples of how to determine if we have outliers outside of 3 standard deviations. This will be slightly different than the IQR method, but for the most part, we should get relatively the same results. If you end up having any outliers that are outside of 3 standard deviations from the mean, in our class, we're just going to remove them from the data set. And then typically what you would do in like a research paper, if you're writing a manuscript, you would say, if this is the statistical analysis we did, in the results section, you would then say that like this was your original sample size. Due to the fact that your data were not normally distributed, you removed values until you got a normal distribution. And then you would report that in your results section. Or you would report how your sample size changed. I do want to point out, though, that we don't always want to remove outliers. So if you recall that like a sample size of 30 typically is considered large enough to the point where we can just assume we have a normal distribution based on that sample size. So I'm going to say, relatively speaking, if you have a sample size less than 30, you would want to do the normality check, make sure you don't have outliers. If you do have a sample size of 30, I think it's a good thing to check normality and to see if you have outliers, but kind of take that information with a grain of salt. Because sometimes, like the Shapiro-Wilk test, it'll tell you that your data are not normally distributed when they actually could be normal. Same thing with the z-skew and z-curt calculations. So that's why we have the central limit theorem. That's why it exists. Right? If you have a large enough sample, you can reasonably assume that you have a normal distribution of your sample data. I still think it's good to check for both of these things, so we'll continue to check for these in the data sets that we have. But if our samples are larger than 30, usually we'll just be like, we'll take it with a grain of salt. So I'll give you examples of those as we go through this semester, but just as a note for now. The other assumption that we need to have is what types of variables we're working with. So you need at least 2 variables to run a correlation. That's our bivariate correlation. You could have more than 2, so that's why I just put greater than or equal to 2. They need to be continuous variables, meaning that they're on some scale of ratio or interval data. So they can assume practically any value within that range. And the last assumption we need to have for a correlation is that they need to have a linear relationship. So because we are running a Pearson's correlation, that is based on the fact that you have a linear relationship with your variables. And again, the quickest way to check for this assumption is to just make a quick scatter plot and see, do we generally see a linear trend in an upward or downward direction? Or maybe we get a scattered section like this where we could draw a straight line through the center and then we see no relationship. If you get outcomes that look like this, right, where the data seem to be curving or something like that, those are nonlinear. And in that case, Pearson's correlation coefficient isn't the best test to use. So there are other analyses that we can use for curvilinear relationships like these, but they're beyond the scope of this class. We like to keep it simple. Linear relationships are kind of more what you guys might be dealing with in kinesiology. An example of a curvilinear relationship might be VO2. So if you're increasing, say, running speed, or you're increasing the work rate, you might see this like inverse exponential relationship of an increase in VO2 as someone approaches a steady state of exercise. That would be one example. Okay. But for the most part, if you're looking at two variables for our class, they should match this linear relationship assumption in order to run a Pearson correlation analysis in SPSS. So that's linear relationship assumption. Once you meet all your assumptions and everything checks out, you can determine, I want to run a correlation analysis. And then it's important to know what the null hypothesis is that you're testing. Okay, so the research question should be somewhat related to the fact that you want to see if there's a significant relationship between a given independent variable or dependent variable. Again, if you have a bivariate correlation, it's just going to be two variables. You want to know the relationship between those two. If you have a multiple correlation, you might want to know the relationship between a bunch of variables. So this is kind of loosely written just because it's open to what you're actually interested in looking at based on the research question. Again, for our class, we look at non-directional hypotheses. So the null hypothesis or a non-directional null hypothesis for a bivariate correlation would be that there's no significant relationship between the two variables of interest. The research hypothesis is mutually exclusive to that. So instead of saying no significant relationship, you do find a significant relationship. And generally speaking, we insert, once we do our interpretations, we'll insert the strength and the direction of the relationship that we find. But as a starting point, the null hypothesis says there's no relationship. And this is the hypothesis that we will be testing in our outputs, right? So we get a p-value, and based on that p-value, we can determine if we have a significant relationship or not. Okay, so again, our hypothesis, two-tail, non-directional. The null would be saying basically that r is equal to 0, right? Because the 0 r coefficient tells us there's no relationship. The research hypothesis would say that r is not equal to 0. So that can range anywhere between +1 and -1, but not include 0. Okay. The p-value is going to be the probability that the null hypothesis is true or the probability that there's no correlation, right? So when we run our statistics, we'll get a significance column or a p-value column in our output, and that will tell us, right, is the relationship or is the correlation coefficient that we found significant or not. And I have an extra note down here, is that p-value indicates the significance of the relationship, not the strength. I do get some people who are like, the p-value was 0.05, therefore the relationship was weak. Okay. Or the relationship was not significant, therefore it's weak. And that's not an accurate statement. Okay, so recall, the value of r gives you the strength of the relationship, right? So if you have like a 0.78, that's a strong relationship versus a 0.25 is a weak relationship. The plus or minus determines the direction of the relationship. So do you have a proportional increase in one variable as the other one increases? Or do you have a negative relationship whereas one variable increases, the other one decreases? Okay, so positive, negative tell you the direction. And then the p-value just tells you if that relationship is statistically significant or not. Okay. The way that we determine significance is still the same as when we talked about hypothesis testing in our previous lectures. So if you have a p-value, well, it also depends on your level of confidence. If we set our level of confidence to 95%, which we're going to do for the rest of the semester, then we're comparing a p-value to an alpha of 0.05. Right? So if our p is greater than 0.05, we say there is no correlation or we accept the null hypothesis. If we have a p-value less than 0.05, we reject the null hypothesis and we say that there is a significant relationship, and then we just determine, or we add in, is that relationship strong or weak or moderate, and is it positive or negative? I do have some examples of this, so if you're feeling a little lost right now, rest assured we will cover some more information. I do want to go through what correlations look like in SPSS, so I've included some screenshots that might be of assistance to you. We will also have examples of this in the activity videos, but if you like screenshots to go back to instead of watching the process through video, that's also cool. But to get to a correlation, we have inputted all of our data. It should be all set to scale type data, so with the little ruler icon, because that would tell us that we have either ratio or interval, right, or parametric type data included in our set here. We would go to Analyze, Correlate, and Bivariate to get to our correlation analysis. And then once you activate the analysis, you should get a box that looks something like this. In this box, you'll have any of the variables that exist in your data set. The variables box, you're going to put the variables you actually want to analyze. Okay, so I have insert the variables you want to include in the analysis. That would go in this box here. Okay, you need at least 2 variables for the analysis to work. So you might have 2 variables, you could have 10, you could have 20, it just depends on what you want. The correlation coefficients that we're calculating for this class are Pearson correlation coefficients, so that should be the default, but just make sure that is the only box checked in that section. And then we want 2-tailed tests of significance. So again, our correlations aren't saying there's going to be a positive, there's going to be a negative, we just say, is there a relationship or is there not? And then also make sure this box at the bottom is checked to flag significant correlations. What this will do is it'll put an asterisk next to your p-values in your output if they're less than the alpha that you set prior to the test beginning. The alpha level is set in the options box. Default for SPSS is 95% level of confidence, so your alpha split between 2 tails should be 0.05 or 0.025 in each tail. Okay. We don't really mess with that because the default is what we want. So after you get to this point, you can basically click OK to generate your output for your correlation analysis. From there, you'll get something what is known as a correlation matrix. And this is generally the setup that you'll get for each variable listed in the table. Okay, so the row name will be split up. So if you all of these things would be included for one variable, let's say, or the relationship between one variable and another variable. You'll get a Pearson correlation coefficient, which is just the value of R. Okay, the sig column, recall, is where our p-value is located. So this will tell us if we have a significant R value or not, or a significant relationship or not. And then n is going to be the number of paired observations that we included, so sample size. This is what it actually will look like. So you can see this example is from the Laird Statistics website that I like to use as a resource for this class a lot. But in this particular instance, we were looking at time spent watching TV and a person's cholesterol. Okay, so for this relationship between these two variables, we can see that the Pearson correlation coefficient R is 0.37. Okay, so that's going to say, in this case, that it's greater than 0.3, so we'll say we have a moderate relationship, and it's a positive number, so we have a positive moderate relationship based on R. Okay. The sig rho is our p-value, which in this case we would want to list the p-value as less than 0.001. Reason being is that SPSS has a rounding. It's not an error, it's just the default settings for SPSS. It'll always give you 3 decimal places for the p-value, and there's never going to be a 0% chance of error. So we never should be reporting a p-value as equal to 0. We always have to say there's some degree of error. We're just limited on the output value. So if you ever get something that says 0.000, don't put p equals 0. You just put p is less than 0.001. Okay, so you're still indicating there's some level of error that's possible. We just don't know the exact value of the error that exists. N would be our sample size, so this means we had 100 paired observations between these two variables, right? We collected time spent watching TV for 100 people, and then we also measured cholesterol concentration for 100 people. That's what we mean by paired observations. Okay. The interpretation of these results, or an example of how you might write these, is because we have a p-value less than our alpha of 0.05. That's indicating we have a significant relationship, right? So the interpretation of this is that there was a statistically significant moderate positive correlation, so moderate positive is from our R value, between daily time spent watching TV and cholesterol concentration. They also included who their sample size was, and then this is how they reported their statistics. Okay. The value in the parentheses is your degrees of freedom. We don't really go through how to calculate degrees of freedom for correlations because we're not going to be using correlation tables to estimate p-values, so we won't really go into that. But usually it's R with your degrees of freedom, your correlation coefficient value, and then the p-value that was associated with that. They decided to report it as p is less than 0.0005. Like I said, if you guys only get this information, you would only put less than 0.001. So this would be an example of how we interpret a bivariate correlation matrix. Sometimes, though, if you have multiple variables that you're analyzing, you would get something that looks more like this. This is a correlation matrix that I generated in Excel. We'll go over examples of how you can make a correlation matrix in the activity videos. But basically what you're doing is you're saying what is the relationship between all of these different variables, and the right half is empty because it should be redundant with the lower half. Right? If we're looking at the relationship between weight and age here, in the matrix, if we also looked at the relationship of weight and age in this box, that value reported in this box should be the same as the value reported in this one. So really you only need to focus your attention either on the top half or the lower half. It doesn't matter which half you look at, you should get the same results. The only limitation with calculating correlation coefficients in Excel is that you only get the R value, you don't get a P value. So if we wanted to know if a relationship was significant, we would have to run our analysis in SPSS. If you just want to know what the correlation coefficient is, you can quickly determine it in Excel. Another note on the correlation matrix is that the values on the diagonal have an R of 1 because they represent bivariate correlations between the same variables. So if we're looking at age and age, right, if we took, theoretically, somebody's age and we plotted it against their age, and we get a point, and we did that for everybody, we would get the exact same increase in y as we do in x. Okay, so that's why they're perfect correlations of 1. So this entire diagonal doesn't really carry any value or weight in our correlation analysis because they're representing correlations with the same variable. Okay. From correlations, or from R, we can also calculate what's known as the coefficient of determination. This is also termed as covariance, which will pop up in next week's lecture on regressions. But what this coefficient of determination is, it represents the common variance, or the percentage of variability that is shared between two variables. So if, let's say, we have an R of 0.7, or a strong relationship, and we squared 0.7, or R squared, we should get 0.49. Okay. We can multiply this decimal by 100 to create a percentage, and then interpret that 49% of the variability we see in one variable is explained by its relationship with the other variable. We could put this as the dependent variable and independent variable, but again, in correlations, if you're not too worried about which variable is independent, which is dependent, this could kind of be interchangeable. For regressions, the order does matter, but we will go back through that next week. Okay. The rest of the percentage that's not accounted for, so 1 minus 49, or 1 minus 0.49, or 100 minus 49%, is what we call the coefficient of non-determination. Okay, and that is the probability that our relationship is due to chance or other factors that haven't been considered. So to put this in terms of variables, I've used the exact same example that we showed on previous slides, where we're looking at the relationship between the time spent watching TV and cholesterol concentration. I've highlighted our Pearson correlation coefficient, so R is 0.371 in this scenario. If we squared that value, we end up getting a value of our squared value of 0.14, and if we multiply that by 100, we get the percentage of variability. So the way that we would interpret R squared, or 14% in this case, is that daily time spent watching TV statistically explained 14% of the variability in cholesterol concentration. The coefficient of non-determination would be 1 minus R squared, so we could either do 1 minus 0.14, or we can do 100 minus 14, and we end up getting 86%. That coefficient of non-determination would tell us that 86% of the variability we see in cholesterol concentration is explained by error and or relationships with other variables. Okay. The reason I chose cholesterol concentration in this instance is because that's kind of like the variable we would try to be determining. Also, this was the example that the Layered Statistics website gave, so I just kept it consistent with that. All right. If numbers don't make a whole lot of sense for coefficient of determination, I have given you guys some examples of Venn diagrams, because these are also like a nice visual way to interpret coefficients of determinations. So if we have two variables that we're comparing to each other, let's say variable A and variable B, we get a correlation coefficient R, and we square that R. That R squared is representing our covariance, or our coefficient of determination between those two variables, and that would be the overlap that exists between the two variables. Right, so this purple area here is equal to R squared. Okay. The amount of overlap is going to tell us kind of how strong the relationship is, or how much variance is explained from one variable based on its relationship with another one. So if we have zero overlap between variables, that would mean we have no relationship. right? Because if r is equal to 0 and we square 0, r squared would be 0. So no relationship, no overlap. If, however, we have a perfect correlation, right, which we have deemed that r would be either positive or negative 1 in a perfect relationship, if we square our r and we end up getting 1, what should end up happening is that we have a perfect overlap between the variables. In other words, 100% of the variability we observe in one variable is explained by its relationship with the other variable that we've compared it to. Okay, so that concludes our lecture on correlations, and I will see you guys in the activity videos where we actually get to mess with numbers and conceptually figure out how this all works.